The telescope is without doubt one of the most important scientific tools ever created. With its introduction, observers for the first time had the ability to see astronomical sights like planets and moons with much more clarity. This single device helped to start the so-called scientific revolution of the 17th century, which helped dispel many of the incorrect scientific beliefs of the time. The great scientist Galileo is credited with being the first person to use a telescope for scientific research in astronomy. With his improvements on the design of the telescope in 1609, he was able to begin making astronomical findings that would change our understanding of our place in the universe. The scientific revolution had begun, pushed forward by the telescope. Telescopes changed very little until the late 1670s, when Sir Isaac Newton designed the first reflecting telescope that used mirrors, rather than an optical lens used in Galileo's refracting telescope. This new type of telescope once again changed the way that scientists observed our universe. Although telescope designs have obviously become much more advanced since the time of Galileo and Newton, the basic principle of how they work hasn't changed. I spoke with Dr. David Gilman from NASA Langley Research Center to talk about telescopes and find out how they work.
Well, a lot of people think that telescopes are used to magnify the image of the sky, but actually for astronomers that's not how they use telescopes. They're used in two ways in astronomy, and the first way is really just to gather light. Some stars are very faint things. You can't even see them with your naked eye. And they have to gather a lot of light so that their instruments can maybe tell something about it from its color or from how it changes brightness over time. This takes a lot of light for something that might be halfway across the universe. The other thing that astronomers use telescopes for is to get an image of what is going on around the object of interest. It might be a spiral galaxy, or it might be remains of an exploded star, in order to see how the pieces are related and affect each other. And here, magnification can make a difference, but normally that's not the principal characteristic people are looking for in telescopes.
Can you explain to me the different types of telescopes?
Although you can make telescopes of any combination and call it a compound telescope, primarily there are two types. The first type of telescope is a refractor telescope. It's made of lenses, and you kind of see its image when you see a pirate holding a spyglass to his eye. That's a refractor telescope.
Yes.
But principally, astronomers use reflecting telescopes. They have these big curved mirrors to gather the light and create the image.
Understanding how a telescope works is simple if you think about it like this. Everything that humans can see is brought to the eyes by light. A telescope is very simply a device that can gather much more light than the human eye can alone. In a refracting telescope, it gathers light with a large lens called the objective lens, while the reflecting telescope gathers light using a primary mirror. Although both types of telescopes accomplish the goal of collecting light, they do it in different ways. In a refracting telescope, the objective lens is located at the top of the structure. This large lens collects the light, then directs it to the focal point inside the telescope. On the other end of the telescope, a small eyepiece lens then brings the image from the focal point to your eye's pupil. This type of telescope works well with smaller telescopes, but making large glass lenses to exacting standards can be difficult. Because it is relatively easy to make large mirrors, most of the telescopes used for scientific measurements are reflecting telescopes. The reflecting telescope works by collecting a large amount of light onto its primary mirror. It then reflects the light back up to a secondary mirror that is angled to reflect the light into an eyepiece. Now, the eyepiece is key for both types of telescopes because magnifying lenses are embedded inside, allowing the image to be easily seen. The larger the lens or mirror in the telescope, the more light that can be gathered, providing a very bright, detailed image of the cosmos. I know that we have ground-based telescopes. Why do we need telescopes in space like the Hubble?
Well, space is really the ideal environment for a telescope. It turns out that if you look at a telescope and look at a star and magnify it as much as you can, all you see is a big, fat, blurry dot, all because of the turbulence in the atmosphere. But in space, that is gone. And we can make telescopes that can have image quality of 1,000 times better, in principle, 1,000,000 times better.
Wow.
And with that, we can see down into the hearts of galaxies and find out what's going on to make some of them active and some of them exploding and many of the other things that we're interested in. So that's one reason to go into outer space. The other reason to go into outer space is that if you're on the ground, you're limited to what the air will let through. It turns out that as you go towards the ultraviolet, the ozone blocks it. That's a good thing because we don't want to get burned with ultraviolet light from the sun.
Sure.
But it's a bad thing when you're trying to find out about the ultraviolet light from stars. There's only a relatively narrow, what we call a window, that is, you can see through the atmosphere, which extends somewhat from the infrared to somewhat in the ultraviolet. But to really explore the entire spectrum of electromagnetic radiation, you have to be in space.
You sometimes hear that telescopes can look back in time to the beginning of the universe. Can you explain that to me?
Well, it's a little bit like the way we hear sounds that were created a little while ago. Sometimes you can see that if you see somebody practicing tennis at a distance, you'll see the ball. And a little later, maybe a second later, hear the bang. And same thing happens with light. It turns out that the light from the moon takes a little bit longer than 1 second to get here, so you're looking back approximately 1 light second when you look at the moon. When you look at the sun, that light left 8.5 minutes ago or so. If you look out at the nearest star, the Alpha Centauri, well, that's like 3 years ago since that light left. It's just only has a certain maximum speed. And so you're always looking back in time when you are seeing even you. It's a little bit back in time.
You're freaking me out. So, Dr. Gilman, do you think that telescopes have reached their limits?
Telescopes have a lot more work left to do. Now that we have completed Hubble and are moving into the next generation of telescopes like the James Webb Space Telescope, we expect to explore the universe in the infrared. Just as the atmosphere here on Earth blocks what we can see, so there are grains in the space between the stars, small particles the size of smoke particles, that block the light coming to us from stars. But infrared light gets through it. So the next round of telescopes are going to exploit this window of visibility in the universe around us. NASA is really leading this exploration. It is a great endeavor of discovery that is going to lead us to the edges of the universe and find out about these forces and what makes the universe the way it is.
So that's how it works. So the next time you want to look out into the universe, reach for your nearest telescope and check out some heavenly bodies.